Welcome back, Chemistry Theory. This is the EC1.2, balancing redox equations by using the oxidation number method. So we looked at in EC1.1 how to determine oxidation numbers using those rules that we had. And now we'll look at balancing equations using the oxidation numbers in our favor. And then EC1.3 will also be another method of balancing redox equations using the half reaction method. So complete and balanced redox equations using the oxidation number method. Some redox reactions are difficult to balance using the conventional methods that we've used back in Science 10, Science 9, Physical Science 20, etc. For this reason, you need to learn a different balancing technique for redox equations that's based on the fact that the number of electrons transferred from atoms must equal the number of electrons accepted by other atoms. Okay, it's just like money exchange. If someone is giving up money, someone must be gaining money. As you know, when an atom loses electrons, its oxidation number increases. So it wouldn't hurt to write this down. So if you look at that number line that we had, let's see, 0, 1, 2, -1, -2. So if I'm going this way, if my oxidation number gets more positive, that means Leo, right? Lose electrons, oxidation. Because if you lose negatives, you're getting more positive. Whereas if we're getting more negative, that means we're gaining electrons. So gain electrons, reduction. So when you lose electrons, the oxidation number increases, meaning it gets more positive. When atoms gain electrons, the oxidation number decreases, meaning that it gets more negative. Therefore, the total increase in oxidation must equal the total decrease in oxidation of the atoms involved in that particular reaction. The balancing technique called the oxidation number method is based on that. Okay, so if one thing is gaining, something else must be losing. So the steps to look at that: assign oxidation numbers to all atoms in the equation like we did in the other section. Identify the atoms that are oxidized and the atoms that are reduced. Again, we did that in the previous section. Determine the change in oxidation number for the atoms that are oxidized and the others that are reduced. Again, we did that in the other section as well. The new part here will be this: make the change in oxidation numbers equal in magnitude by adjusting the coefficients in the equation. So here's where the balancing comes into it. And then if necessary, to finish it off, you may have to use conventional methods to balance, just like we did back in previous science courses, Science 10 and Physical Science 20. So look at this example and run through all those steps. So balance the redox equation shown here for the reaction that produces copper and nitrate. So copper and nitric acid giving copper 2 nitrate, nitrogen dioxide, and water. So you could try it by conventional means like you would in previous courses, but it may be a little difficult. So and it is, because if you look at over here at NO3, NO2, so you have the NO3 breaking off, making some NO3 here plus NO2, so it's a little tricky. But oxidation numbers using that method makes it a lot easier. Okay, if we turn to the flip side, what I'm going to do is just rewrite it so we have a lot of room to do it and to take a look at it, because the font is kind of small on the previous page. So we'll just look at it over here. All right. So first of all, assigning oxidation numbers, right? So copper is just simply by itself. So there's an oxidation number of 0 each one, which means that there's a total of 0. Oxygen, as we were told, it has an oxidation number of -2, but I have 3 of them here, so -2 times 3 is -6. Since this compound doesn't have a charge, we know that it must add up to be 0. Hydrogen, unless it's a hydride, unless it's at the end of the compound, we know it's +1. So that tells us what number we require here to make this a true statement. So 1 plus 5 minus 6 gives us 0. And of course, I only have 1 nitrogen, so that 1 nitrogen must be +5. Over here, oxygen, again, is -2. Now, if we look at what I have here for oxygens, I have 3 oxygens here, but I have 2 sets of 3. 2 times 3 is 6. So I actually have 6 oxygens there. If each oxygen is -2, 6 times -2 negative 12. And again, I don't know, or sorry, there's no charge here, so it's going to be a minus, or sorry, a 0. Now, it seems kind of tricky. Now, where do I go? Now, you know from this, since I need two nitrates to balance one copper, I know that that is copper 2. And that gives me the response for what the oxidation number must be. Plus 2. It's a plus 2 for copper 2. Okay? And then that'll tell me what I need here. So 2 plus something minus 12 equals 0. So we know that's going to be a plus 10. So nitrogens contribute plus 10. How many nitrogens do I have? I have 2 nitrogens. So those 2 contributing equally to that plus 10, then it must be plus 5. Okay? And over here, oxygen's negative 2. 2 times 4 is negative 4. Or sorry, 2 times 2 is negative 4. I know that has to add up to be 0. So that means that this nitrogen must be 4, and there's only one nitrogen, so it's 4. And water must be plus 2 here, so each hydrogen is plus 1. All right, so you've assigned all of the oxidation numbers. Now we'll take a look at what's changing here. So we know copper is changing. It's going from a 0 to a 2. And from our previous page, when I'm getting more positive, lose electrons, oxidation. So it's oxidized. And the net change that happens here, we're going from 0 to plus 2. So that's a plus 2. Oops. Okay, let's take a look at what else is happening. This nitrogen to this nitrogen, there's no difference, right? Plus 5, plus 5. But if I look at this nitrogen to this nitrogen to this nitrogen, I'm going from plus 5 to plus 4. That's getting more negative. So gain electrons, reduction. If I'm getting more negative, I'm gaining electrons. And going from plus 5 to plus 4, that's a net change of negative 1. All right, so negative 1. So that was the first step that I needed to do. So if I look back at this paper here, so determine the change, make the change in oxidation numbers equal. So I'm at step 4. So the net change here is plus 2, net change here is minus 1. So to make this equal, of course, the lowest common multiple of 2 and 1 is 2. So if I can have 2 of these, I'll get a net change of negative 2, which matches a net change of plus 2. So to do that, to make this doubled, what I need to do is adjust the coefficients in the equation. So instead of having one nitrogen go to one nitrogen, I'm going to have 2 nitrogens going to 2 nitrogens. So over here, HNO3, put a 2 in front of here, saying that I need to double it, double the negative 1. This stays the same, and now doubled here. Okay, so that means I'm getting closer, right? 1 copper, 2 ends, but yeah, look at here, 2 times 2, 2 times 2, I have 4 ends there, so I'm going to have to make a few adjustments here to make this work. And of course, knowing that this nitrogen, or the nitrate, some of the nitrates are unchanged in terms of oxidation or reduction, so that means I need to have more of these NO3s, because for every one that's here, I have 2 going over to here. So by using conventional means, what I can look here is like 2 nitrogens, so that's 4 ends. So if I change that to a 4, 2 of them will be going to here, and 2 of them will be going to here. So change that to a 4, since 2 nitrates are going to remain unchanged, and 2 nitrates are undergoing a change in reduction. So let's see what we got now. 1 copper, 4 H's. Oh, I'm going to have to make 4 H's here. Let's do that. 4 ends, 2 ends, 2 ends, 4 ends in total. And let's look at oxygens. Hopefully they work out here. Over here I have 4 times 3, which is 12 oxygens. Here I have 6 oxygens. Here I have 4 oxygens. 6 plus 4 is 10. And look at that. 2 times 2 oxygens there gives me 12. So there we go, we have it. So we did the redox section of this, looked at the coefficients, then from there, this gives you the setup to balance by conventional means. So what we'll do is we'll stop there. Why don't you try to do this one, and then in the next video we'll see how that one comes in to play.